हेलो माय डियर मैकेनिकल चैंपियंस, हाउ आर यू ऑल? व्हाट्सअप, कैसे हैं सब लोग? माई सेल्फ चंद्रशेखर welcoming you all to this beautiful session of thermal engineering, that is first law of thermodynamics. So you guys are watching me live through the startup series which is running for all the GATE 2024 aspirants. Here we discuss the important concept from a particular subject, as well as we also discuss the numerical sessions, numerical practice sessions as well. So today's session is all about the first law of thermodynamics. Please do let me know if I am audible and visible to everyone so that we can start our session. Those who are watching me live, please do respond through the comment section if my audio and visual quality are fine. So for those who are attending the session for the very first time, this is my quick introduction. I am mechanical engineering graduate from IIT Delhi, having more than 10 years of teaching experience in the field of GATE, IES and PSUs. I have also cleared engineering services examination. I had worked in SAIL for a couple of years and I am quite comfortable in these many areas of mechanical engineering. You can connect with me through the mail ID chandra.shekhar7@byju's.com, or you can join me on the Telegram also, that is Mechanical by Chandrasekhar, and the link is also shared at the bottom of the screen. Once you become part of my Telegram group, you will be getting the important exam notifications, PDF and study notes will also be provided to you, and the information for the daily sessions, free sessions which we take from time to time on the YouTube platform as well as on the app, along with the doubt clarification will also be done through the Telegram group. All right. So can you just let me know if my audio, video all are fine? Tonight at 7:30 p.m. important announcement. There is a free workshop for GATE 2024 aspirants. Asu Jangra sir will be taking this important session. He will discuss about the strategy to get the best possible rank in your GATE 2024 exam. All right. So let us start with the first law of thermodynamics. Are you all ready to explore the beauty of the first law in a different or unique manner? So this is the part of thermodynamics. Thermodynamics is nothing but thermo plus dynamics. What is thermo? Thermo is energy. Dynamics means motion. Hi Harry. Hi Bepili. Welcome. Good evening. Thermodynamics is nothing but energy in motion. So what does that mean? In thermodynamics, we study the energy transfer which can take place either in the form of heat or the work, and the effect of this energy transfer on the properties of the system, right? That is known as thermodynamics. So we will be talking about the energy transfer through the first law of thermodynamics. Now, a system and the surrounding. Do you know what is a system? What is surrounding? A system and the surrounding interacts with each other in two ways, either in the form of mass transfer or in the form of energy transfer, or both. So we are talking about open system. In case of open system, the interaction between system and surrounding can take place with the mass transfer or with the energy transfer. But if it is a closed system, hi Virendra, good evening. If it is a closed system, then the mass transfer does not take place from the system to the surrounding. I hope you guys are aware about that, because I am not talking about what exactly is a system, what is the surrounding, how the interaction, energy interaction or the mass interaction between system and surrounding take place. But the overall picture of the system and surrounding is, a system is a region upon which our study is concentrated, and everything else, then the system is known as the surrounding. So system and surrounding talk to each other in the form of energy transfer from the system to the surrounding or from the surrounding to the system. and they talk to each other in the form of mass transfer. Mass can transfer from the system to the surrounding or from the surrounding to the system. That is about the open system. But if it is a closed system, it means no mass transfer takes place in case of a closed system. For a closed system, only interaction between system and surrounding is through energy transfer, and energy transfer can take place either in the form of heat or in the form of work. The transfer of energy can take place either in the form of heat or in the form of work, isn't it? Heat and work. And if it is an isolated system, do you know what about isolated system? There are three types of system based on the interaction between system and surrounding. Isolated system is no mass transfer takes place between the system and surrounding, no energy transfer takes place between the system and the surrounding. That is called as isolated system. Example is universe. Universe is an example of isolated system. Universe is nothing but system plus surrounding taken together. System as well as the surrounding taken together becomes the universe. So from the universe there is no mass transfer takes place. From the universe there is no energy transfer takes place. So the isolated system does not interact neither in the form of mass transfer nor in the form of energy transfer. All right. Now let us see what is heat transfer. The energy transfer which takes place due to temperature difference. The energy transfer due to temperature difference is known as heat transfer, denoted by Q. And heat transfer always takes place from high temperature to low temperature, isn't it? Heat will always flow from high temperature to low temperature. When T1 is greater than T2, the transfer of heat will take place from T1 to T2. If T2 is greater than T1, then the transfer of heat will take place from the temperature T2 to T1. Very, very important is sign convention, because sometimes the heat is transferred to the system or sometimes the heat is transferred from the system to the surrounding. So whenever the heat is added to the system, it will increase the energy of the system. System is the region on which our studies focus. So whenever the heat is entering into the system, then it will increase the energy of the system. So that will be taken as positive. And when the heat is rejected from the system, it will decrease the energy of the system. That will be taken as negative. So that is about heat transfer, denoted by Q. That is one form of energy transfer. The another form of energy transfer is the work transfer. So in a simple words, what we can say, all the other forms of energy transfer other than heat transfer are known as work transfer. All the other form of energy transfer, other forms of energy transfer are called as work transfer. All the other forms of energy transfer are known as work transfer. For an example, if there is an electrical energy transferring to the system, so we will call it as electrical work transfer. If some mechanical energy is getting transferred, then we will call it as mechanical work transfer. If there is some chemical energy getting transferred from the system to the surrounding or from the surrounding to the system, we will not call it as energy transfer. We will not call it as heat transfer. We will consider it to be the work transfer. And when the work, the technical definition of work transfer is this one. Work is said to be done by the system if the entire effect on the things which are external to the system gets reduced to raising of weights. The weights may not be actually raised. So that is the technical definition. But how do we separate the heat from work? When the energy transfer is taking place due to temperature difference, it is considered to be the heat transfer. And when the energy transfer is not taking place due to the temperature difference, it is called as work transfer, right? and the sign convention says work is done by the system on the surrounding is taken as positive, whereas the work done on the system is, sol means entire, sol means complete effect or entire effect, right Virendra? So work done by the system is taken as positive and work done on the system is taken as negative. So what I have discussed so far is the interaction between system and surrounding happens in two ways: mass transfer and the energy transfer. And energy transfer can also be divided into two parts, either in the form of heat or in the form of work. Heat transfer is happening when there is a temperature difference, and all the other form of energy transfer happens when there is no temperature difference or without the temperature difference, right? And the mass transfer can also take place. If it is an open system, there will be mass transfer, but if it is a closed system, then the mass transfer will not take place between the system and the surrounding, only the energy transfer will take place. And if it is an isolated system, insulated system is different. Thermally insulated system means there is no heat transfer. Insulated is not same as isolated. Insulated is not equal to isolated. When we say isolated system, mass transfer will be zero, energy transfer will be zero. When it is insulated system, then the heat transfer will be zero. Only heat transfer will be zero. There is a difference between insulated and isolated system, right? So let us talk about the first law. We are ready to explore the first law of thermodynamics now. One important announcement: we are going to start a series for all the GATE 2020, all the GATE previous year from 2019 to 2023 onwards, starting from the 5th June. That is going to help you all if you are preparing for GATE 2024 examination. So do join our this series to get maximum benefit out of it, right? So what do you understand by the first law of thermodynamics? Can you let me know what exactly is the first law? What do you understand when you hear about the first law of thermodynamics? First law of thermodynamics is nothing but energy conservation law. It is also known as Joule's law. It is also called as quantitative law. Why do we call it as quantitative law? Have you heard about that? The first law of thermodynamics is nothing but energy conservation law. We can also call it as Joule's law because Joule was the first one who gave this law. And it is also known as quantitative law because energy is having the quantity, magnitude as well as the quality. So the first law of thermodynamics does not talk about the quality of energy. It only says the quantity of energy remains constant. The energy conservation means the energy always remains constant. Energy can neither be created nor be destroyed, but quantitatively. Qualitatively, there is a degradation of energy that we will discuss in second law of thermodynamics. All right. So according to energy conservation, can we simply say for a system, can we say some energy will be entering? Can we say some energy will be leaving? So can we say the energy entering into the system minus energy leaving from the system is nothing but change in energy in the system? Some amount of energy will enter into the system, some amount of energy will leave from the system, and the difference of these two, energy entering is like your income, energy out is like your expenses. Your income minus expenses is your saving, isn't it? Can we say that? The energy entering into the system minus energy leaving from the system is nothing but change in energy of the system. So let us try to understand the significance or importance of these parameters LHS as well as RHS. Let us talk about the RHS first. What exactly is the energy change of a system? What do you understand by the change in energy of a system? What is change in energy of the system? Look, when it is a simple compressible system, we are talking about compressible system in thermodynamics. In fluid mechanics, we talk about incompressible system or incompressible fluid. Simple compressible system. For a simple compressible system, change in energy of a system is equal to change in internal energy of the system plus change in potential energy of the system plus change in kinetic energy of the system. This is called as microscopic energy because it is associated with the molecules. The energy is stored inside the molecule that increases the internal energy of the system. It is called as microscopic form of energy. Microscopic. And the rest of these two are known as macroscopic. Macroscopic because they are associated with the particles. They are associated with the system. Change in potential energy of the system, change in kinetic energy of the system. So the total energy change for the system is microscopic energy change plus macroscopic energy change, right? If it is a stationary system, the system is stationary, there is no change in potential energy, there is no change in kinetic energy. For a stationary and simple compressible system, we can say change in energy of the system is nothing but change in internal energy of the system. U is called as internal energy. U is known as internal energy of the system, which is associated with the molecules of the system, right? That is why it is known as microscopic. Now, what is the energy transfer E in minus E out? That is the energy transfer from the system to the surrounding or from the surrounding to the system. So we can say E in minus E out. The energy interaction takes place in the form of heat transfer, right? So we can say Q in minus Q out in terms of heat transfer. It can take place in terms of work transfer, W in minus W out, and it takes place in the form of mass transfer, or there is some energy associated with the mass transfer. So we can say energy in along with the mass transfer minus energy out along with the mass transfer. So the total energy interaction will take place in three ways. One is in the form of heat transfer, another is in the form of work transfer, and the third one is associated with the mass transfer, along with the mass transfer. Do you know that if there is a mass transfer taking place from the system to the surrounding, there is some energy associated along with the mass transfer that is represented by the third term. And if it is a closed system, try to understand, if it is a closed system, what about the mass transfer? Do you agree mass transfer will be equal to 0? I had already told you. For a closed system, the mass transfer will be 0. And if the mass transfer will be 0, so this term will become 0. Do you agree or not? For a closed system, the third term will be equal to 0. This is the first term, this is the second term, this is the third term. Do you guys understand it or not? Please give me yes. So can we say energy entering into the system minus energy leaving from the system is simply Q in minus Q out plus W in minus W out. That is for a closed system. Can we call it as right? This is the expression. So for the first law of thermodynamics, which involves LHS and RHS, the energy interaction between the system and surrounding is equal to change in energy of the system. That is what we have discussed about. The change in energy of the system is simply the potential energy change, kinetic energy change, and the internal energy change. The energy transfer is along with the heat transfer, along with the work transfer, and along with the mass transfer. And if it is a closed system, there is no mass transfer taking place. So we can say the energy transfer is with the heat transfer and with the work transfer only. Now let us modify this first law of thermodynamics. What is the first law of thermodynamics? Says E in minus E out is equal to change in energy of the system. That is the basic energy conservation equation. When it is a closed system, do you understand mass transfer will be equal to 0? For a closed system, mass transfer will be 0. And if it is undergoing a thermodynamic cycle, do you know thermodynamic cycle? For a thermodynamic cycle, the initial and final points remain same. So do you agree, for a thermodynamic cycle, delta E, change in energy of a system undergoing a thermodynamic cycle, will be 0. So we can say E in will be equal to E out. Or we can say the total energy entering into the system, so we can say Q net, the net heat transfer, is equal to W net, net work transfer. That is the first law applied for a closed system undergoing a thermodynamic cycle. Or we can say sigma Q net is equal to sigma W net, because energy interaction will take place in the form of heat transfer and in the form of work transfer. So net heat transfer should be equal to net work transfer. Or we can say cyclic integration of del Q is equal to cyclic integration of del W, because heat and work are path function, they are not property. So this equation is valid only for a cycle. This is another way of representing the first law of thermodynamics applied for a closed system undergoing a thermodynamic cycle. So net heat transfer will be equal to net work transfer. It is valid only for a cycle, not for a process. And the cycle can be reversible or irreversible. The cycle, thermodynamic cycle, can either be reversible or it can be irreversible. Do you understand it? So either we say, look, let me take an example. If there is a system undergoing a thermodynamic cycle 1 to 3, so Q1 to 2 is positive, heat added to the system, Q2 to 3 is negative, heat rejected from the system, and Q3 to 1 is also positive, heat added to the system. Then work done during this cycle, let me take an example. Work done W1 to 2, it is positive because it is done by the system. W2 to 3 is negative because it is done on the system, and W3 to 1 is again positive because it is done by the system. So we can say Q net is equal to W net. These are used along with sign. This expression will be used with sign. They must be used with sign. So we can say Q1 to 2 minus Q2 to 3 plus Q3 to 1 should be equal to W1 to 2 minus W2 to 3 plus W3 to 1. That is the first law of thermodynamics applied for a cycle. Or we can write it as the total, or one is this way, Q net is equal to W net. Or we can write it as all the heat entering into the system. What is E in? Can we say E in is equal to Q1 to 2 plus Q3 to 1 plus W2 to 3? And what is E out? What is the energy leaving? Energy leaving from the system is Q2 to 3 plus W1 to 2 plus W3 to 1. 1 to 2, 2 to 3, yes, W3 to 1. If we equate this, E in is equal to E out, we will get the same result. Q1 to 2 plus Q3 to 1 plus W2 to 3 is equal to Q2 to 3 plus W1 to 2 plus W3 to 1, isn't it? So either we say E in is equal to E out, or we can say Q net is equal to W net for a thermodynamic cycle. And if it is an isolated system, I told you E in is minus E out. E in minus E out is equal to change in energy of the system. That is our first law of thermodynamics. For an isolated system, there is no energy entering, there is no energy leaving is equal to 0, or we can say Q is equal to W is equal to 0. So if this is 0, then from the first law of thermodynamics we can say delta E is equal to 0, or energy remains constant. The total energy of an isolated system always remains constant. The energy of an isolated, because isolated system does not involve any mass transfer, does not involve any energy transfer. So the change in energy of an isolated system does not take place. So for an isolated system, the energy change will be 0, or the isolated system will have constant energy throughout. On 4th of June, there is a scholarship test. Do attend this scholarship test. Based on your performance in the scholarship test, you will be able to avail the discounts on our various paid courses. So you can register now to be part of this test and get benefits. Right? And for the link is already there in the description box for registering yourself for the scholarship test. After the class, please go through the description box once to get the important links. Now, if we talk about a process, the first law applied to a non-flow process. What is non-flow? It means closed system. The process undergone by a closed system. It means there is no mass transfer. Mass transfer will be 0. And as we know, energy in minus energy out is equal to change in energy for a system, isn't it? So it is either in the form of heat and in the form of work, because there is no mass transfer taking place. So if we write this, then we can say Q in minus Q out plus W in minus W out is equal to, we can say delta U plus delta potential energy plus delta kinetic energy. This is the expression, first law, for a non-flow process. And or we can write it as, this is Q net is equal to delta U plus delta PE plus delta KE plus W out minus W in. That is called as W net, because heat added to the system is positive, heat rejected from the system is negative, work done by the system is positive, work done on the system is negative. So we can say this is W net. So we can say Q net is equal to delta U plus change in potential energy plus change in kinetic energy plus W net. This is another way of writing our energy conservation equation for a closed system undergoing a process. And if there is no change in potential energy and kinetic energy, if it is a stationary system, for a stationary system, can we say Q net is equal to delta U plus W net? Do you agree? For a stationary system, Q net is equal to delta U, change in potential, change in internal energy plus W net, that is the net work transfer. Use with sign. All the parameters should be used with the sign. That is the first law applied to a non-flow process. And if it is applied to the flow process, there is mass transfer takes place in the flow process, or we can call it as open system. Flow process means open system. There is a mass transfer along with the energy transfer. That is the difference between closed system and open system. So there is a mass transfer. So we can say M in minus M out is equal to change in mass in the control volume. The way we write the energy transfer and energy conservation is E in minus E out is equal to change in energy in the control volume. For the flow process, we use the control volume approach. We define a control volume if there is a mass flow taking place. So this is the energy conservation equation. Mass conservation and energy conservation equation can be written like this. And this energy interaction is along with the heat transfer It takes place along with the work transfer, and the energy transfer takes place along with the mass transfer, isn't it? It takes place along with the mass transfer. Now the flow process can be divided into two parts. One is called as steady flow process. What is the steady flow process? When the parameters does not change with time. No change with respect to time. That is called as steady flow process. For a steady flow process, we can say mass flow rate remains constant. M dot in is equal to M dot out remains constant. Or we can say the change in mass per unit time in control volume will be equal to 0. That is the mass conservation for a steady flow process. For a steady flow process, change in mass in control volume will be equal to 0. So M dot in is equal to M dot out. Rho 1 A1 into C1 is equal to rho 2 into A2 into C2. Mass flow rate entering will be equal to mass flow rate leaving. C is the velocity of flow and A is the flow area and rho is the fluid density of compressible fluid or density of the system, right? And if we talk about the energy conservation for a steady flow process, when the flow process is steady flow process, look, U is internal energy, it will be replaced by H. This is the internal energy which will be replaced by H. Are you getting it? Why? Because H involves U plus PV. What is PV? That is called as flow energy. The energy associated with the mass flow, that is called as flow energy. I told you that whenever there is a mass transfer taking place from the system to the surrounding, along with the mass transfer, there is an energy transfer associated, and that energy transfer is called as flow energy, which is associated with the mass transfer. So internal energy will be replaced. Our earlier equation was Q net is equal to delta U plus W net. Do you remember? So delta U will be replaced by, or we can say earlier equation for a closed system, it was, first law was Q net is equal to delta U plus delta PE plus delta KE plus W net. So here U will be replaced by H. So energy conservation equation will be Q net is equal to delta H plus delta PE plus delta KE plus W net. That is for steady flow process. That is the energy transfer. If we write per unit time, delta H is H2 minus H1. Potential energy M into Z into Z2 minus Z1. Isn't it? Change in kinetic energy half into M into C2 square minus C1 square. We can write H can be written as M into H2 minus H1, specific enthalpy. If you write per unit mass, if we write it as per unit mass, then we can say H1 plus C1 square by 2 plus GZ1 plus QCV is equal to H2 plus C2 square by 2 plus GZ2 plus WCV. This is the energy conservation equation for a steady flow process. What do we call it as? Steady flow energy equation. And what is the unit of each and every term? It is joule per kg. This is known as steady flow energy equation. That is how we obtain the steady flow energy equation for the steady flow process, right? And if it is unsteady flow process, then the things become little more complicated. Every Saturday we are bringing some more fun learning concept, interesting to make your learning more and more interesting. One series is the Knowing the Legends, where we will be discussing about the various scientists, their biography, their achievements, etc. And another one is the Raftar series, which is about the technology related to the automobile sector. So that has already been started. So please do subscribe our BYJU'S YouTube channel and do not forget to like this session so it reaches to all of your friends and colleagues who are going to appear for GATE 2024 exam. All right. So let us talk about the last thing, That is the first law of thermodynamics applied to the unsteady flow process. Unsteady flow, when the change with respect to time. Changes with respect to time. Like the examples of unsteady flow process: charging of a rigid vessel from a supply line, discharging of a fluid from a pressurized vessel, inflating a balloon. This is our control volume, let us say, and the control volume is undergoing a process 1 to 2 due to some fluid entering at inlet, fluid leaving at the exit. I for inlet, E for, let us say, exit or outlet. 1 is the initial state and 2 is the final state. These are the notations. These are the notations we are going to use to develop the expression. So if we talk about the mass conservation, there is mass is non-zero. The rate of change of mass is non-zero, or we can say m in minus m out is equal to change in mass in control volume. That is the mass conservation. Mass conservation equation is simple. M in minus M out will be equal to change in mass in the control volume, or we can write it as Mi minus Me is equal to M2 minus M1 in the control volume. Can we write this way? This is the mass conservation equation. So Mi will be equal to 0 when no mass enters the control volume. Me will be equal to 0 when no mass leaves the control volume, isn't it? And M1 is equal to 0 when the system is initially evacuated. System is initially evacuated, right? And Me is equal to M2 is equal to 0 when the system is finally evacuated. So one or more terms can be 0 based on the given condition. This is about the mass conservation. And if we write the energy conservation equation for this, then we can say, what is our energy conservation equation? What we know is Q net is equal to delta H plus W net. Now, in case of this was for a steady flow. For unsteady flow, there is, or we can say, our basic energy conservation equation was E in minus E out is equal to change in energy of the system or the control volume. So if we write it, then we can say Q net, that is the heat entering into the system. I am writing Q in, the E in, that is plus Mi into Hi plus Ci square by 2 plus Gzi minus this, let me write it as W net minus Me He plus Ce square by 2 plus Gze is equal to change in energy of the system. Can we write it as delta U plus delta Pe plus delta Ke? This will be the expression. And if there is no change in potential energy and kinetic energy, potential energy and kinetic energy, if there is no change, if there is no change in potential energy and kinetic energy, then our equation will become, Q net plus Mi into Hi minus W net minus Me into He is equal to M2U2 minus M1U1 in control volume. This is our energy conservation equation. Small u is called as specific internal energy. This is called as specific internal energy, and H is called as specific enthalpy per unit mass. So this is how we can write the energy conservation equation for a known as for a flow process which is unsteady state flow process. All right. So that is all from my side for the day. On Friday again, I will be coming for second law of thermodynamics. And on Saturday, we will be having the practice session for the first law as well as the second law. You can connect with me through the mail ID. Thank you for joining in. And now is the time to say you goodbye for the day. Do join me on the Telegram, that is Mechanical by Chandrasekhar, and stay connected. See you in the next session. Till then, enjoy, take care, have a good day and a great career ahead. Thank you guys. Thank you for joining in. Take care.